Hi everyone, welcome to today's live broadcast, Explore the Benefits of Empore Membrane Solid Phase Extraction Products in Lcgc Sample Preparation. I'm Alyssa Maripodi, the custom content writer of Lcgc, and I'll be your moderator for our event today. This webcast is presented by Lcgc and sponsored by CDS Analytical. CDS Analytical is a leading global provider of innovative thermal sample preparation instrumentation for the analytical laboratory. For 50 years, our exclusive focus has been on conceiving, designing, manufacturing, and servicing GC sample introduction instruments, including pyrolyzers, perch and tap, headspace, and thermal desorption systems. In 2019, CDS purchased the Empore solid phase extraction product line from the 3M company. Now, CDS continues to use the same formula and manufacturing process to bring users the same historic, trusted quality of the Empore brand. For more information, visit cdsanalytical.com. We have a few important announcements before we begin. This webcast is designed to be interactive, so we encourage you to ask questions during the event. You can submit them by typing them in the Q&A box that's found on the right-hand side of your screen. You can enlarge the slide window by clicking on the small square icon in the upper right-hand corner of the slide window, or by hovering your mouse over the lower right-hand corner and dragging the window to the desired size. The slides will advance automatically during the event. If you have any technical problems viewing or hearing the presentation, click on the question mark help widget in the dock at the bottom of your presentation window. I would now like to introduce our speaker for today. We are pleased to be joined by Michael Apsicardou. Michael is the Empore product manager at CDS Analytical. He holds a doctorate degree in chemistry from the University of Delaware, and he has over 6 years of experience in chromatography and mass spectrometry analysis, and now uses his background to support the designing and testing of new technical applications for Empore at CDS Analytical. Michael, thank you for joining us today. Please get us started.
Hi, welcome to this live Lcgc webcast. My name is Michael Apsicardou, and I'm the product manager at CDS Analytical for our Empore solid phase extraction product line. Today I'm going to be talking about Empore and its membrane technology and the benefits to Lcgc sample preparation methods. So everybody is familiar with sample preparation and how important it is to an overall sample analysis. Most of the time that you will spend on analysis will come in the sample preparation stages. In fact, that's about 60 to 80% of your total time. So of course you're spending so much time in the sample preparation stage that you're going to run into a lot of roadblocks and you're going to make a lot of mistakes. So about actually 30 to 50% of the errors that you're going to make will come during sample preparation. And then there are also a lot of other difficulties that come along with sample preparation as well, including the difficulty of separating your analyte from its matrix and any contaminants and interferences contained within the matrix. So this may include salts or biological substances such as tissues, proteins, enzymes, or phospholipids. And then maybe other chemical constituents that are undesirable as well. And then, of course, another difficulty is always sensitivity, not having a high enough concentration of your analyte to measure it with the analytical instrumentation. So this could either be because your analyte's not concentrated enough and you need to increase the concentration, or these interferences are interfering with the signal of your analyte, reducing your sensitivity and your effectiveness to measure your target. So the success of an analysis is really going to heavily rely on the sample preparation stage, where you need specific high throughput procedures to improve your sensitivity and also improve the separation of your targets from these different interferences that are undesirable. So if we look at the landscape of sample preparation techniques, it can be kind of crudely separated out into a two-dimensional space where we have a least specific and going to most specific on the x-axis, and then on the y-axis you have a slowest to going up to the fastest technique at the top, or the most expensive at the bottom, and then also the cheapest at the top. So starting with the least specific and the cheapest and the fastest, this is going to be the dilute and shoot method, where there's no separation that's even done. What you have, your target and your sample matrix, just go right into your analytical instrumentation. As we start to get a little more specific, we start to get to procedures that do require some kind of separation. So this includes protein precipitation, centrifugation, and filtration. But if we go to the other end of the spectrum where we actually start to rely on chemical interactions to dictate and regulate the separations that we're interested in, we can look at liquid-liquid extraction. This is the most specific, but the downfall of liquid-liquid extraction is that it's slow and it's very expensive to perform. And then along with that, just a little quicker, a little less expensive, but also a little less specific, is solid-supported liquid-liquid extraction as well. So then, of course, as a sample preparation technique, you just want everything, something that's in the sweet spot, right in the middle of specificity, cost effectiveness, but then also time that it takes to perform the methods. This is where solid phase extraction comes in. It's right in the sweet spot, right in the middle of all three of those key parts to having a successful sample preparation method. So for SPE sample preparation, this basically comes down to having a liquid or a gaseous substance pass over a solid sorbent that your analytes are going to adsorb and cling on to in the solid phase. So the benefits that can be gained with SPE are you can isolate and concentrate your analytes, thereby eliminating the matrix and any of its potential interferences, and you're preparing the analytes for your final analysis. So the basic procedure for performing solid phase extraction comes down to starting with the picture at the bottom, starting on the left with the first step, the conditioning stage. So in the conditioning stage, you can see you're preparing your sorbent, which is shown here as kind of a purplish color. You're preparing this for an extraction. In the second step, you're going to load your sample, which contains two key parts for this example, which is just going to come down to either your target analytes or your interferences. So as your target analytes and your interferences pass over the sorbent, everything is going to be interacting to the sorbents, but the idea with solid phase extraction is that your analytes are retained and your interferences are released. They pass through the sorbent and are released out the bottom of the cartridge, which is what you can see for the purple and the blue circles coming out the bottom of this cartridge. In the third step, you can see this is a wash step. This is where you remove any of the remaining interferences on the sorbent, and you can see now that the analytes are still retained on the sorbent, so now you have complete separation of analytes and interferences. The fourth step is the elution step, where you elute the target analytes off the sorbent and you collect them. From here, you can either evaporate or reconstitute if either of them are necessary, and then go on and do your final analysis. There are different types of solid phase extraction labeled on the left-hand side over here. So we'll start at the very top with reverse phase. A reverse phase is really going to rely on nonpolar interactions. So you could think of this either as the van der Waals forces or pi-to-pi interactions. There's also normal phase solid phase extraction. This is going to be polar interactions coming from primarily hydrogen bonding or dipole-dipole interactions. There's ion exchange, cationic or anionic, and then there's also mixed phases as well. So this is going to combine the ionic exchange with either nonpolar or polar sites as well. So we can take a look at some of the basic sorbents that can be used for examples of reverse phase extractions here, which is primarily what I'm going to be discussing today. So if we start on the left-hand side, you can see that for nonpolar extractions, we have C18 and C8 sorbents. And then if we move more towards the middle, towards moderately nonpolar and moderately polar sorbents, we have a mixed phase cation. So this is that mixed mode sorbent that contains actually a C8 chemistry combined with strong cation exchange. And then there's also something we call a universal resin, which is a really versatile sorbent, really well designed for acids, bases, and neutral compounds. An SDBXC, the SDB is styrene divinyl benzene. And then very similar to that sorbent is an SDBXD. And then also a styrene divinyl benzene RPS. The RPS is reverse phase sulfonated. So this is going to be another mixed mode sorbent combining that styrene divinyl benzene chemistry with the strong cation exchange. And then right in the middle, for polar compounds with reverse phase extractions, we have an activated carbon disc, perfect for highly to moderately polar compounds. And then in the far right, we have strictly ion exchange. At the bottom, you see there's an SCX. This is strong cation exchange, chelating for multivalent metal ions, and then SAX, which is strong anion exchange. And there's two primary bases for these sorbents that you can have, and they're kind of color-coded here in this figure. Sorbents are either commonly silica-based, which are our gold sorbents here, or they're either polymer or resin-based, which is the red here. So getting specifically to the Empore membrane and its technology highlights, this is formally really referred to as a particle-loaded membrane. So this particle-loaded membrane technology was originally patented and invented by the 3M company, and it was purchased by CDS Analytical in 2019. So that's why this 3M is featured on top of this stylized membrane that you see right in the middle of the screen. So what is this membrane technology? It really is sorbent particles that are tightly bound and mixed in with the polymer backbone. So they're so tightly held together that this really confines the sorbent and the polymer to a small space, and the thickness of the membrane is actually only 0.5 millimeter in thickness. So some of the unique features of this membrane are its high uniformity and its high density. So the uniformity and the high density are really well combined to optimize flow rates through the membrane to improve and make faster the procedures that you're performing in the lab. But then also the high density makes the particles really closely packed with each other. This mitigates the effect of channeling that you often see with other methods of SPE, such as loose packed SPE. In fact, the extraction efficiency of the Empore membrane technology is about 5 times higher than that of traditional loose packed SPE. Other advantages that can be gained with the high density membrane are, again, with so many sorbent particles confined to a small volume, you can effectively reduce your sample volume and reduce your elution volume, like you see in the upper right-hand corner of this slide. And again, as a function of the high uniformity and the high density, the sorbent particles are very tightly packed into the membrane. You really reduce the amount of fine particulate matter that's shedding off of this membrane. This is really key to extending the lifetime of your LC equipment. So the Empore membrane is really high capacity, and this slide gets a little bit more into actually the composition of the membrane. So the sorbent particles, as I mentioned, are held together, tightly packed in with this polymer backbone, which is actually polytetrafluoroethylene, or PTFE. So by mass, it's about 90% sorbent, 10% PTFE. And you can see two microscope images of the two bases of the sorbents that you commonly find, either silica-based on the left or resin-based on the right. So the membrane technology can vary in density, and when we say vary in density, this means that it's varying in the average diameter of the particles, the sorbent particles going into the membrane. So we have what we refer to as a high density containing particles that are 8 to 16 micron in diameter. Having these smaller particles really is meant to optimize your extraction efficiency. And then you have a standard density, which has larger particles on the order of 30 to 60 micron. And having these larger particles really helps to optimize the flow through the disk. So you can really time save by having faster flow rates through the disk, which is, again, is a function of the high uniformity and the high density of the Empore membrane. So clogging and slow flow through the disk are common problems that you also often find with other conventional types of SPE. And you can see a small little table here that actually compares those flow rates with some of those conventional methods. So the Empore membrane can have flow rates between about 300 and 700 milliliters per minute. So this is actually about 2 to 6 times faster than what you would have with other conventional types of SPE. So a concern might be, we have such a fast flow rate, does this negatively impact the recovery or the extraction efficiency? You can answer that question by looking on the right-hand side here, where you can see that picture from a few slides ago showing the uniformity of the disk. The example here is for the extraction of a red dye, and you can see that the extraction is so efficient that the dye is limited really to the very top portions of that Empore membrane with no channeling of the red dye down into the lower parts of the disc. So what this means is that this extraction example was done at 700 milliliters per minute. So you can have these high flow rates going through the Empore disc without compromising your extraction efficiency. And then to come back to the elimination of fine sorbent particles from SPE products. This is again a key feature of the high density membrane where you don't have the shedding of these products for Empore, which is what you can see in these microscope images for samples A through C, and then Empore as the lower image, the image in the lower right. So for samples A, B, and C, you can see that there are a number of different fine particles that clearly appear in these pictures. Empore really has nothing that's there. In fact, if you compare Empore again to a traditional type of SPE, such as loose packed SPE, it's about 1/10 of the shedding of the material from the SPE product. So this is hugely important to sample preparation procedures and your overall analysis because this really helps you avoid clogging of maybe columns and then also avoiding instrument downtime. So now I want to take a look at some specific applications. So this is first looking at a application tree or decision roadmap for large volume samples. So this is going to be of interest for primarily SPE formats of either disks or cartridges. So for the purposes of this presentation, the sample volumes are greater than 100, we'll say. And this is a generalized roadmap meant to be really a guide for this presentation. Some of these categories find their way to only one sorbent for the applications we're talking about here. But in reality, this is a generalized conceptual map. So there may be more than one sorbent that's effective for some type of chemistry or application that you're interested in. So what I want to look at first is starting right in the middle for water testing. So the way that I want to look at this application roadmap is you start right here with water testing, and you're going to branch from there to your different types of potential applications, which could in this case either be drinking water or groundwater. So what this application roadmap does from there is in the case of wastewater, will bring you down to a specific application concerning wastewater, which would be hexane extractable materials, and then from there show you what a recommended product would be for this type of extraction. So this would be a special product that we have called the oil and grease disc, and then also shown along with that is the EPA standard method that goes along with this oil and grease wastewater testing. So I'm going to talk about a specific example in this application, and then also talk about a specific example for the extraction of semi-volatile organic compounds, also for water testing as well. So the drinking water testing side is a little bit more complicated because there's a wider variety of molecules that could be contained under the umbrella of drinking and groundwater. So this includes moderately polar, moderately nonpolar compounds. So this could include pesticides or organohalides, nonpolar compounds, including PAHs, PCBs, phthalates, mixed phase, which is good for explosives in water, nitroamines, nitroaromatics, other types of pesticides. And then we also have ion exchange with our chelating, our strong anion exchange and strong cation exchange, and then polar with the activated carbon. So now we'll have just a couple examples on large volume testing. So what you can see here is a list of EPA methods for water testing. And what you can see on this list is on the left-hand side is the number of the application or the written procedure from the EPA. There's a number of EPA methods listed here, maybe about 10 to a dozen methods listed here. There's a lot more than that that are not shown on this slide. So there are a lot of EPA methods that are compatible with solid phase extraction. So the list that's here covers a wide variety of different chemicals, including phthalates, nitrogen, phosphorus, chlorine-containing pesticides, polycyclic aromatic hydrocarbons, PCBs, and then also one specific application, EPA method 525.3 for the extraction of 125 different semi-volatile organic compounds in water. So you can see that also on the right-hand side, there's also a recommended SPE disk that goes along with each of those different methods. You can see that many of them are either C18 or SDBXC, but the Empore membrane technology is compatible, is a verified product for these EPA water testing methods. So to take a look at some specific applications, this first application is for that method that I just mentioned previously, EPA method 525.3, for the extraction of SVOCs using the SDBXC disk. So in this procedure, these SVOCs are contained within a water sample. That water sample is passed through the SDBXC disk, and the SDBXC disk extracts those SVOCs, which are then eluted and reconstituted and analyzed via GCMS. So then on the left-hand side, you can see that chromatogram for 125 different analytical standards under this method. And from that extraction, all of those different standards are able to be chromatographically resolved, and the peaks of each standard has good resolution as well. And also you can see that the baseline is very clean and there's very little noise, which is definitely a product of having a good extraction product as well. So a key part of this method is to quantitatively determine the concentrations of these different targets in this water sample. So what was done for this work, and what you can see on the right-hand side, is for samples of reagent grade water with 3 different concentrations of SVOCs, and then 1 sample of groundwater. We're really interested in what the extraction efficiency or recovery is of these SVOCs from this sample. So there's 2 key things that are of interest for quantifying, for reporting here. The first one is how many analytes have a recovery that's greater than 70%. So 70% is the lower allowable limit for this method as defined by the EPA. And then also the average recovery of all of the SVOCs from the extraction. So you can see for the greater than 70% recovery, at least 118 of the SVOCs are recovered with these high recoveries for each of our different samples. And in all 4 cases, the average recovery is at least 90%. So as a result, kind of what this says about the SPE disk is that this is a really good sample preparation method for improving volume throughput to analyze a large volume of water very quickly, but then also having a product that can give you a clean extraction that also will give high accuracy and high reproducibility as well. So this next example is another EPA method, 1664, which extracts hexane extractable materials, or HEM, using the oil and grease disk. So this is really a gravimetric analysis determining the mass that you recover of the HEM, and then determining the recovery from there. So what you can see in the table on the far right column is you can just look at the average recovery at the bottom of that table, and you can see that the recovery is nearly 100% with a very good percent RSD. So again, this shows that using the sample preparation of SPE, these oil and grease disks can be very effective extracting this HEM material and having very high recoveries along with very high reproducibility. So then, of course, it's always of interest to try to improve throughput as much as possible. So also as part of this work, what was actually done too is that there's also SPE workstations that are available to help you process multiple disks and cartridges at the same time. So for example, on the right-hand side there, this work was done with the Empore EasyTrace workstation that conveniently allows you to analyze at least 4 disks at the same time while simplifying operation and making it very easy to collect waste and also collect your eluate. So this is a really good way to help improve your throughput of your samples at the same time. So I want to come back to the decision-making tree and go on to our next application section, which is on the left-hand side here for the special application of LC mobile phase cleanup. So in terms of LC mobile phase cleanup, kind of what this means is purifying maybe your aqueous mobile phases that are going to be important to your HPLC methods. So often what you find is contaminants in your mobile phases, and this could be phthalates, plasticizers, or even detergents or anionic surfactants. So we're going to look at a specific application for analyzing the effectiveness of the SDBXC disc for removing contaminants such as phthalates or plasticizers. So this is some work that was done to purify LC mobile phases with the SDBXC disc. What you'll be able to see from this is that the SDBXC disc is very effective at removing contaminants from aqueous mobile phases, more so than other purification procedures. So if we look at the figure on the left, what you can see are 3 chromatograms that are overlaid on each other that were subjected to different purification procedures. The very top one used a glass fiber filter, the one in the middle used an activated carbon, and the bottom one uses the SDBXC disc. What you can see is that the glass fiber and the activated carbon are not able to remove these interferences that are present in the mobile phases, so you can clearly see those in the chromatogram. On the other hand, the SDBXC disc proves to be very effective at removing these contaminants that would otherwise greatly interfere with your LCMS analysis. In the right-hand figure, what you can see is different HPLC methods, 4 of them, versus the percent of the contaminants that are moved. So these are all aqueous mobile phases that were purified here, and they differ from A to D in terms of decreasing pH. So D has the lowest pH of the 4 mobile phases. So this is a comparison of the activated carbon with the SDBXC disc for removing those contaminants. And the SDBXC disc in each of the gray bars, you can see removes nearly 100% of the contaminants for each of those different mobile phases. Whereas the activated carbon, as the mobile phase gets increasingly more acidic, the activated carbon does worse of a job as it gets more acidic. So what you can see is that the SDBXC is also effective for removing contaminants from different types of mobile phases as well. So now continuing in that application example, this is actually adding in some target analytes to your mobile phase to see if you can remove the contaminants and chromatographically resolve those targets that you've spiked your samples with. So again, this uses the different preparation procedures of the glass fiber, the activated carbon, and the SDBXC disc for 8 different targets. So pretty much in all 3 cases, you can see that targets 1 through 6 can all be chromatographically resolved. Although with the glass fiber, it's starting to get a little interesting because you can see that the baseline is starting to creep up pretty high, especially for that number 5 target analyte. It's really when we get to analytes 7 and 8 that you start to see the effect of high baselines and insufficient removal of contaminants, that you see the kind of the benefit of the SPE disc in this application realm. So you can see from the glass fiber filter and the activated carbon that those contaminant peaks are pretty high, and neither of them see target number 7, and 8 is not really well resolved, especially for the glass fiber. Where, on the other hand, the SDBXC disc significantly reduces the baseline, removes the contaminants, and you're able to chromatographically resolve both peaks 7 and 8 here. And it's also really important to point out here that purifying your mobile phase using the SDBXC disc doesn't interfere with your retention time, and it also doesn't affect the resolution of your peaks. So I want to come back to the large volume sample decision-making tree one last time and just point out a couple special applications with some special sorbents that we have. So one of them is a special application with two sorbents called the RP1 and the SDB-XD. These have found a really special application for particularly non-ionic surfactants. The other special application is for radiochemical testing for water samples. So Empore actually has SPE discs that are specifically designed to extract radiochemical species for radium, strontium, technetium, and cesium. So this is of interest to applications such as the Fukushima site in Japan. So about a decade ago, there was a nuclear event that occurred, and there was a nuclear fallout there. And basically, since then, the Fukushima site has been flowing water over this nuclear reactor to maintain some stability of this reactor. And they've been storing this water for about a decade now, and there's plans to release this back into the ocean. After a series of testing and confirming that this water would be safe by the Japanese government. But there are some concerns over the safety of the water by scientists and locals. So, of course, there needs to be testing methods to be able to measure the concentrations of specifically strontium and cesium in this case. So this is a special application for a radiochemical SPE sample preparation procedures for the Empore membrane technology. So the next thing that I want to go on to is for small volume decision making. So this is another application tree for a few different application sections here. For the first one on the left being proteomics, the one in the middle being a combination of pharmaceutical, clinical diagnostics, and toxicology, and then the one on the far right being food and natural products. So I'm going to spend very little time in the section of food and natural products. So I just want to kind of go through some of the different things that you will see, the different analytes and the different sorbents that could be effective in the food and natural products realm. So if we start on the far left of food and natural products, right here with nonpolar, some of the things that we might be interested in extracting are toxins, antibiotics, or even maybe some vitamins like B and D, which the C18 sorbent could be effective for. Or then going on to the right, moderately polar, nonpolar, could be analyzing for flavor compounds coming from alcohols, esters, or aldehydes and ketones. And this is good with the SDB-XC for extractions. Ion exchange with strong anion exchange, maybe for organic acids and pigments. And then also measuring moderately polar to polar compounds as well, such as mycotoxins and vitamin K, using a silica gel-based sorbent. So most of the applications that I'm going to be discussing are going to fall into the rest of this application tree, starting here with some examples in the pharmaceutical and clinical diagnostics toxicology realm, looking at some examples with the C18 phases, the C8 phases, and SDB-XC. So the first example that I will look at is actually a clinical testing example. So this is work that was conducted by the World Anti-Doping Agency for testing for 31 anabolic steroids that are on the prohibited list. So in the figure on the left, what you can see is that there was a comparison of signal-to-noise ratios that was done for the Empore C18 extraction cartridge versus another type of conventional SPE. So after extraction, all of these different anabolic steroids were measured via GCMS, all of the extractions occurring from urine samples. So what you can see right away is for both Empore and the conventional SPE method is that for all of the anabolic steroids, they all have sufficient signal-to-noise ratio that you would need to quantify the signal. So this shows the effectiveness of the Empore membrane technology, though still from being able to extract from biological samples such as urine and give a good recovery such that you have good signal-to-noise ratio to quantify. But if we want to look at the differences between the Empore membrane technology and the conventional SPE, we can look at the far right of this figure where you see the red box. This contains the different steroids where Empore significantly increased the signal to noise ratio over the other type of SPE. So this work really breaks down this comparison as either those that Empore and the other SP method are similar, and those that Empore had a better signal to noise ratio. So if you combine all of those, the Empore procedures in this particular work produce similar or improved results for about 80% of all the different analytes tested. So you can see an application here where the C18 sorbent would be effective for the extraction of chemical substances such as steroids. In this next example, we have a clinical assay for Gleevec. So Gleevec and its metabolite are of interest specifically because Gleevec is an inhibitor treating acute myeloid leukemia. So this analysis is an SPE LCMS MS analysis of monkey plasma using the C8 96 well plate. So if we look at the results, right in the middle, we have the recovery for 3 different concentrations. The average recovery is 70%. And then at the bottom, we have accuracy at the limit of quantification and above the limit of quantification. And in both cases, the accuracy is right around 100% with very good coefficients of variations here. So what you can see is that the C8 well plate technology is very efficient at improving sample throughput to do a lot of analyses in a short amount of time. But also the Empore membrane technology is efficient again for extracting analytes from biological matrices. Also, this example uses less than 200 microliters of solvent to elute and also achieve a high recovery. So this is really important to improving your sensitivity because lower elution volumes really help to concentrate your sample, and you can avoid unnecessary evaporation or reconstitution steps. The next example is a clinical toxicology example looking at microcystins. So the microcystin of interest here is the autoamino acid. So the interest with microcystins is that they're present in water sources and they target the human and animal livers. So this is an SPE LCMS analysis quantifying MMPB, which is just an oxidation product of that autoamino acid. So this extraction is done with the SDBXC cartridge. And what you can see is that the recovery is 93%. So you have a very good, very high recovery. So you can quantitatively recover markers for toxins using this SDBXC disc. Also, what you find from this application is that the SDBXC disc is able to remove other interferences that other types of conventional SPE were not able to. So this next example is a clinical testing example, specifically for antimicrobial drugs. So the specific examples here are for fluoroquinolones, which are antimicrobial drugs administered in human and vet clinics. So this is another SPE LCMS analysis, extracting these drugs from urine. So this is using this mixed mode sorbents that I had referred to earlier, specifically our MPC sorbent, which is the C8 or the SCX combined to a silica-based sorbent. So this MPC is really good for removing these types of antimicrobial drugs, or also has applications to drugs of abuse. So what you can see in the bottom right-hand corner are the recoveries, and you can see that these recoveries that were achieved between 46 and 65%, these were the highest recoveries of a number of different conventional SPE methods that were tested. So what we can see is that the membrane technology here is good at being able to extract and recover these types of analytes from biological samples such as urine samples. So now to come back to the application roadmap for small volume decision making. The next application that I want to look at is going to be in the proteomics phase. where we're going to look at a couple specific examples for how the membrane technology can benefit proteomics workflows. So what I want to look at here is for nonpolar adsorbents. You can see that for proteomics, you're going to have applications to peptide and protein desalting or peptide enrichment, and then even in anion exchange, which I'm not going to really talk about today, applications in fractionation as well. So in this next example, this is an actual example for a peptide analysis, analyzing and quantifying biomarkers for preterm birth. So this is an SPE LCMS analysis of serum samples using the C1896 well plate. And the use of the 96 well plate in this specific application is actually for desalting your samples. So this is really important for being able to quantify the results, and you can see the two figures on the left-hand side showing the calibration curves for both peptides. So you can see that the calibration curves are very linear with very high R-squared values showing the effectiveness of the C18 well plate for desalting the samples here. So this is really crucial for the sample preparation of biological samples where you want to quantify via LCMS analysis, and salts would negatively impact the ability to quantify the peptides that the scientists were looking for in this specific application. The other thing about desalting is that it's necessary for protecting your LCMS equipment. So you gain advantages for being able to quantify your sample, but also you reduce the risk of damaging your LCMS equipment significantly. The next example is in clinical proteomics, which is for high throughput phosphoproteomics. So this is a look at phosphoproteomics for HEPA cells 1 through 6, comparing a traditional method for phosphoproteomics sample preparation and analysis compared to a stage tips procedure. So what are the stage tips? You can see an actual example down in the bottom left-hand corner here. These are actually users in the lab who have acquired the Empore membrane disc technology and then separately acquired micropipettes and have used the discs to put Empore membrane technology into the tip of a micropipette. So this has a lot of advantages to reducing volumes, to desalting, enrichment, and even fractionation. So what you can see in this work is a comparison of traditional processing methods compared to the stage tip methods and the benefits that can be gained by using the stage tips that contain this Empore membrane technology. So in the traditional method, this begins with lysis and solubilization, and then going through your steps of labeling, digestion, desalting and lyophilization, fractionation, enrichment, and then LCMS analysis. You can compare this to the sample preparation and analysis procedures using the stage tip, where this again begins with lysis and solubilization, followed by digest, and then enrichment by titanium oxide. And then moving from there to the next step, enrichment with the 96 well plate. So in each of these well plates are pipette tips that contain the C8 Empore membrane technology. So the C8 Empore membrane technology is used here to enrich and concentrate the peptides for LCMS analysis, before this goes on to a final step of elution and desalting. So this reduces the number of steps in the traditional method using the stage tip method, and we can also compare this to the conventional method and see that some of the benefits that are gained are that with the stage tip method, you use 10 times less starting material. The measurement time and analysis time is 3 times faster. And then also the data quality improves as well. With the stage tip method, you're actually able to quantify 3 times as many sites as you do with the traditional method. The last application example is for desalting of peptides in COVID-19 fast detection. So this is work that was done by the Mayo Clinic just here in 2020, of course. So this figure is put together by the Mayo Clinic, showing kind of the whole sample preparation procedure, going from the collection of the swab through the heat inactivation to the immunoassays before running the sample on the Orbitrap for high resolution mass spectrometry. So before the samples are run on mass spectrometry, there's some desalting steps that are run using a piece of equipment that contains a way to automate these stage tips to desalt and improve throughput of the samples very rapidly. So what you can see with this tip is that this is a tip that contains the C8 Empore membrane technology right at the very tip of it, and this is used for desalting applications. So this has a lot of benefits. Obviously, removing the salts benefits both your quantitative analysis, but it also benefits the lifetime of your LC equipment. But then also these tips are disposable as well, so this prevents cross-contamination of your samples. So this is a very effective method that has a very high sensitivity, very high specificity, and then also has very high throughput for samples as well, all in part because the Empore membrane technology facilitates a desalting step in this wildly important analytical procedure. So in summary, SPE is used in a number of different applications and can benefit users in all of their sample preparation procedures in these different spaces, including toxicology, pharmaceutical, proteomics, food and agriculture, and even large volume sample analysis procedures for environmental work, or even just for purification of LC-MS mobile phases. Some of the key features of the Empore membrane that I discussed today were the high uniformity and the high density of the membrane, which really improves and optimizes the flow rate of liquid through the membrane, but also reduces the channeling effect, so it's improving the interactions of analytes with adsorbent particles. So this in turn reduces the elution volumes, and also the benefits of the high density is that it also reduces the amount of fine particles shedding from the Empore membrane. So all in all, with all of these features combined, the benefits that can be realized with the Empore technology are high recovery and high reproducibility, and also just higher throughput of your samples altogether, whether that's increasing sample throughput or increasing the flow rates of liquid through the Empore membrane. And then also another benefit is that with reduction of the fine particles from shedding, you can avoid clogging and LC downtime as well. So I'd like to thank you for your time and attention today, and I'd also like to thank all of our distributors here in the United States for supporting us and supporting our product line, and you can find them available through all of these different channels. Thank you.
All right, thank you, Michael, for your presentation. Before we get started on the question and answer session, I would like to remind our audience that you can submit questions by typing them in the Q&A box that is found on the right-hand side of your presentation window. Our first question today is, what are the benefits of the membrane?
Yeah, so the benefits of the membrane really come down to some of the properties of high uniformity and high density. So this kind of helps to reduce breakthrough of analytes through the membrane, and also help improve flow rates and improve overall throughput and extraction efficiency with the membrane. So some of the advantages that are gained by the high density and the high uniformity, in addition to the high flow rates, are reduced elution volumes and also reduced fine particles as well.
Okay, great. And how does the membrane improve throughput in sample preparation?
So some of the things that I just mentioned about the benefits of the membrane technology also help to improve throughput as well. So throughput is improved by faster flow rates, help saving you time, but then also, again, the high density and the uniformity help reduce processing time of extracts by reducing elution volumes or eliminating the fine particulates that would otherwise require additional procedures to move removed before analysis via LCMS.
Okay, and the Empore member is only 0.5 millimeters thick, which with much less sorbent compared to traditional SPE products. Is there any concern of analytes breaking through?
No, there's no general concern of analyte breakthrough due to the membrane thickness. So again, this has to do with the high membrane density and high uniformity. So because the sorbent particles are packed very tightly into a confined volume, the extraction efficiency is actually 5 times higher than traditional SPE. So really what this comes down to from a chemistry perspective is the membrane really contains more theoretical plates per unit length than traditional SPE does, so increasing that extraction efficiency. So for an example of extraction efficiency, our 3 milliliter cartridge with the Empore membrane, this contains approximately 10 milligrams of sorbent in bed mass. This would be interchangeable with a traditional 1 milliliter cartridge containing 100 milligrams of sorbent.
Okay, and have Empore products been used for post-mortem toxicology, blood and tissues?
Yes, so the Empore membrane has been shown to be effective for toxicological applications. So often mixed mode phases, such as our mixed phase cation phase, is very effective for extracting basic and amphoteric drugs, while maybe like our C18 phase has also been shown to be effective for analyzing or extracting acidic and neutral drugs of abuse as well. In terms of blood and tissues, we have a product such as a 96 well plate containing filtration products to help analyze blood and tissue samples, and then also the membrane technologies to extract different types of analytes from those blood and tissue samples as well.
Okay, the next question says, in the past I used Empore products, but it is very expensive compared to other brands. Not sure if this has changed.
Yeah, so the Empore line has seen significant changes since the acquisition by CDS. So our prices are lower and they're very cost effective compared to other brands in the SPE market now.
Okay, unfortunately we are out of time for today. I want to thank our audience for attending and participating in today's events. I would also like to thank our sponsor, CDS Analytical, for making today's educational webcast possible. We would like to ask everyone in the audience to participate in a brief survey, and you can see the survey to the right of your screen. You will receive an email alerting you when this webcast is available for replay, and we invite you to forward that announcement to your colleagues who could have missed today's live event. Thank you, everyone, for joining us. We will see you next time. Goodbye.